All right, so my name is Tasso Chaudhary, and this is Lab 2 for Physics 2211. All right, so real quick introduction. So, what's the purpose of this experiment? Well, to say it quite frankly, the purpose is basically the compared position of a projectile that's affected by gravity as well as drag, and we're also going to go ahead and compare the real life example we have to a computer simulation and see just how accurate they are. Now, secondly, the method. So, how are we going to do this? Well, it's quite simple. We recorded a video showing one of my colleagues throw a paper ball. All right. And we recorded that video. And then from there, we also had a meter stick showing. So we could also use that to kind of go ahead and create a reference as to how much space is shown in the video. And then we were able to go ahead and upload that into Tracker to go ahead and display the data from the video. Furthermore, we also use GlowScript to create the computational model, if you will. So some of the math formulas that we used, position update formula, velocity update formula, drag force formula, and gravity. Now the question is, why did we use them? Well, it's quite simple. The position one, we needed to be able to move the ball in our code. Otherwise, the ball wouldn't move. The velocity update is necessary to change the ball's speed and direction based on the acting forces such as drag and gravity. So that's why we needed that. Then we also have the gravity. Again, the gravity force pulls the ball down, and we have drag, which basically slows the ball down in the direction of motion, basically kind of makes it more realistic. All right, now going off to it, here is the real life video
Yeah, go
real
ahead.
quick. And as you can see, it went ahead and did two things. We have the X and Y graph right there. And what we're able to show is that the X graph, it's roughly a straight line, linear in a sense. Thus, it's indicating a horizontal velocity is constant. And then we also have the Y graph, which is curved, showing the vertical motion being affected by gravity, as well as from it going from where it originally started all the way to a peak and coming all the way down to its final. Now we're going to go into the code real quick. Now this is going to be real simple. This is showing all the code edits I had to do. Some of the code edits I did was, well, first and foremost, I had to go ahead and change the position, make sure it aligned with the position in my video, which was 0 and then 0.333. You can see right here. And then we also had to go ahead and change the velocity to 1.3 going to X and 2.1 going to Y direction. On top of that, I went ahead and also had to calculate FNet, which I believe is right around here. We made sure that it could have the components of drag as well as gravity included. And then finally, this is just showing some arrows, updating the arrows. And then I believe, where is it? It's B. Yeah. So in this case we had B is equal to 1, but I had another one where I had B is equal to 0 just to show the difference between drag and how drag could affect it. And this is sort of how you can see it. This one right here shows the arrow pointing straight up. This one had a drag force of 1. This one, on the other hand, didn't have drag. The main difference we were able to see is that, well, the one without drag was a lot more smooth and longer, while the one with drag was much shorter and fast. Another key difference is the one with drag is able to show a much more accurate representation of what actually happens in the real world versus the one that only had gravity affecting it. Now, one of the what ifs, imagine if the object was just initially thrown up, straight up. Now, what would happen? Would it be the same, longer, or shorter time than the original experiment? Well, the answer is simple. It would take longer because, again, long story short, when you throw the ball all the way up, it's going up at a constant speed for a while and then it'll start coming down. Essentially, what we're doing is we're giving it more airtime. And because we're giving it more airtime, it takes longer for it to fall. That's about it. Now, I do want to bring up the last part of my experiment, which were some of the possible issues. Some of them were human errors, such as like, dude, it was a paper ball. It wasn't the exact sphere, so that could affect some of the data. On top of that, the tracker data error, going ahead and pressing the tracker and being able to pinpoint the exact location of the ball every single instance was kind of difficult. So that was an issue. And on top of that, if you were to see the tracker data, it wasn't exactly as pristine linear as the computational model. But again, I mean, at the end of the day, these were minute details that really weren't affecting too much. And the other issue I could say would be the timing and data capture, because the beginning and the end, keep in mind the object was already in motion, so we had to be very cautious as to where we could go ahead and have our initial start as well as our final, and that was requiring human decision making in a sense. So basically, I had to use my best what do you call it, in a sense, guess to, hey, this is where it probably is a good part for me to say it started, and this is a good area for me to say it ended, and that could also have played an effect. And that's about it. Thank you so much for watching.